Okay, today we're going to be doing a kinematics freefall experiment, so that way acceleration is constant and velocity initial is 0, and only gravity acts on this little Kirby here. We're going to be comparing time and height, time being the dependent variable and height being the independent variable, and we're going to be seeing what happens to time as height increases. Alright, so setup is very simple. I have my brother down there with a timer and data sheet, and he's gonna time how long it takes for Kirby to fall. I have Kirby here, which I will drop, and a tape measure to measure 5 different heights. This up where I'm standing right now is about 16 feet. This is the 5th height I'm gonna be dropping him from. Procedure is really simple too. On his go, I will drop Kirby, and the moment I let go, he'll start the timer, and the moment he hits the ground, he will stop the timer and record the time. 15 feet, trial 3. Can we all the way? Ready? Go.
1.06.
16 feet, trial 4. Ready?
1.03.
Alright, here is the data table that I drew out. I have 5 heights and 4 trials for each, and I averaged the times at the end to plot that on the graph. Okay, the calculations are used to find the theoretical time it should take to fall with the given height. The equation is delta y equals 1/2 gt, gravity times time squared, plus velocity initial times time. However, the thing is, velocity initial is always 0 since you're just dropping it, and g is always 9.81 since in free fall only gravity acts on the object, which is 9.81. So v initial will cross out. Everything for all 5 of these would be the same except the delta y, which varies depending on what height you're looking at and how long it takes for that to fall. You plug in and solve for t to give your theoretical value. Here's the final data representation as a graph, and this is the original where I just placed my points in. Nothing changed, and here's the line of best fit for it. And here is the linearized version of the previous graph. To linearize it, I just square time, and here you can see the correlation is much closer than the last one. Both the graphs are a position versus time graph, time on the x-axis and position on the y-axis. Time is measured in seconds and height is measured in meters. The heights would have been better if all the meters were actually whole numbers, or at least not decimals, but I had to convert from inches and feet on a tape measure, which made it harder. Graph is linear, which is to be expected. The higher you go, the longer it would take to fall. And here's the percent error calculations, and in these I'm mainly just comparing what the time should be versus what the time I got. The time should be which I got from the calculation, and the time I got from the experiments. Some of these errors are pretty close, like 0.220% error, but then you got other ones like 31.4% error. That's mainly due to human error when using the timer. There's no way for me to press the timer the moment Kirby fell, and there was no way to stop it the moment he hit the floor. So the one where it's 31.4% error, I might have just messed up clicking the timer. And also the heights could be off by some, since the tape measure and me dropping it from that point wasn't exactly perfect. One way I feel like I could improve upon this experiment is if I had a better device for measuring time. Maybe something like a photo gate where it can start a timer the moment I let go and stop it the moment it hits the ground. That would reduce error by a lot, the percent error by a lot, especially this 31.4%, instead of using a cell phone timer. Also, if I had something that actually measured in meters, rather than having me measure in feet and then converting to meters, that would also probably reduce error by some too. I have to say, probably the hardest part of this was actually figuring out what exactly I could do. I don't exactly have a lot of materials at home. I don't even have a meter stick. That's one thing. All I had was a cell phone timer, a tape measure, and how to get one of my little sister's dolls to drop, Kirby. When I thought about it, kinematics was probably the only thing I could do, and mainly free fall, because then that way I knew acceleration was constant, 9.81, and there was an initial velocity that I needed to figure out. So comparing time and height was probably easiest for me to do. I really want to do something like harmonics or pendulums, but I realized I have nothing to make the pendulum or anything like a spring to actually make the waves for the harmonics. So, in conclusion, height and time are directly proportional. As height increases, time will increase as well, and as height decreases, time will decrease as well. And that's the end of the experiment and conclusion.